Get out of my bed to come here, Copper. Hello, Papa.
Almost after.
That's what we were talking about. It's only 10:30 in the morning.
No, she told the lady, have a good night.
Oh, no.
Because I thought it was like 2 o'clock in the afternoon.
I looked around like, it's 10:30 in the morning.
I thought they're so late. I want it to be so late. I just want to go to bed. I like your sweater.
Oh, nice. Not too attractive. Thank you.
And I just went up.
Oh, nice.
I wear jewelry. I can't. It bothers me.
Wait, what's the one about a copper ring?
Tom Brady got his 7th ring
Oh.
this weekend, and I'm very mad about it.
That was funny.
No, leave him alone. He's fine.
Tom Brady?
Leave him alone. Hey, he's chilling.
Mine's down for
I texted my brother and I said, Chiefs aren't looking too hot right now. He was so butthurt.
I don't have to leave phase early this today.
Yes.
Got some burner.
So good.
I'm gonna take a nap instead. Wait, what? Well, after we take a
Phase is like my favorite ones.
No, I'm just tired. Practice this morning really sucked.
Oh,
You
I like
meant,
the-
you meant chemistry is your favorite.
Chemistry is my favorite.
Yeah.
We love
He
chemistry.
clocked.
We all knew what you meant.
Yeah.
It's a big word.
Word association, it's hard for me.
Sometimes I get my.
When I say phase, I mean chemistry, and when I say chemistry, I mean chemistry.
Yeah, everything is chemistry. Boom.
Like there's nowhere else I'd want to spend my birthday at.
See, beats that tanning bed.
Don't do me like that.
Just when you're really hungry.
Feel it like gradually
Yeah, it's great. It's been-
I had a chemical reaction that happened to my skin.
There you
Is that
go.
correct?
Yeah.
As you can see by Shelby's stomach, it's a solution. It's not colored at all. That's why there's some yellow and some red. It's not got some
Ew.
red.
Other parts of her are purple, so.
Oh, no, like. Copper, look at me. Purple. No, it's not even red, it's
Thank you so much
purple.
for
It is
the image.
purple.
Listen, I wouldn't send that video and I wasn't even thinking about you. I was like,
We appreciate it.
Yeah, we talked about that. I was like, did she forget he was in
I
there?
totally didn't even think about it. I was like, it wouldn't even,
That's true.
like, I don't get that.
I hate it when people do that. Like, I just want to wear my bra around sometimes, like.
I don't work like that.
Yes, no, I only wear sports bras, so that's better than sports. I love how everyone on Zoom can just hear us talking about.
Well, don't worry, it's being recorded too.
Oh, good.
Talk about being a tiny
There's
bit.
some more on there.
And running around just our undergarments. Oh, good. Yeah, I love that.
My doctor wished me happy birthday.
That's medical doctor.
I know, right?
Those patient's birthdays off.
Hello?
My ankle is like. Did you see that?
Oh, I see it now. That's something else.
It hurts so bad.
Baseball bat?
A whole lot. Softball. Sylvia's bruising that. You see it from over there?
And I thought it was just pulled it up.
Oh, I'm supposed to go to the trainer.
My dad did. We don't have production, so that's
Oh, nice.
very nice.
That's way better than normal.
Oh, yeah.
And fruit cancel.
Would you like to get?
Yes, we're just zooming in for a little,
Seriously?
yeah. That sucks. No, I'm so excited. I told you I was gonna take a nap.
I hate that.
Poor Copper.
She said she doesn't want us driving or walking on campus.
I always want to be that I can stay the entire time.
Oh. Yeah. All of us on campus anymore. Oh, she's not, okay, that makes sense.
She's not living one of the dorms.
I don't, Bruce, she's my roomie.
What if the professors all live on the dorms? Who would you room with if you had to live on the dorms?
I totally wish Larry Graham had a dorm right next to me.
Would it be Brenneman? Would you room with him?
That would give Howard your own.
Yes, it would. Life of the party, first floor, West Hall.
I'm gonna pass on that question.
Well, you don't have roommates this year, so at least you have your own space.
Yeah, you won't be on your own.
Imagine the West Hall kitchen. It's just.
Just a Chem lab. It's casual.
All right, another question. If you were made of anything other than organic materials, you could choose what you're made of. One element. What would you be made of?
Platinum.
Yeah, okay, Brianna.
What's the good answer?
I would be carbon.
Gotta give me a minute on that one. I actually did a project on if you were to be made of something, you'd like me to pick one. My 7th grade self, I picked strontium. Listen, 7th grade self is arriving.
You know, it's going on campus, just scoffs at you.
Did I say it wrong?
No,
She's confused where she went wrong.
you said it correctly. It's just why you said it, I have no idea.
Listen, in 7th grade, I thought the name was cool, okay?
Okay. All right, we're gonna go ahead and get started here. So can the people on Zoom see my slide and hear me okay?
Yes.
So what we're going to do today is we're going to finish up chapter 13. And then on Thursday of this week, we'll start chapter 14 and then we'll have a quiz on chapter 13. So this Thursday, quiz on chapter 13. All right, so when we left off last class, we were talking about units of concentration. We went through mass percentage, part per million, part per billion. And what I want to do today is pick up on mole fraction and go from there. So mole fraction is simply the ratio of moles of some substance, and it can be the solute or the solvent, versus the total number of moles in a solution. And so to calculate that, whichever component you're looking for, you would calculate the number of moles are there, and then you divide it by the number of moles of that component plus the number of moles of any other component that's in there. And then that gives you that mole fraction value. So if you're going to do this mole fraction calculation, you need to know the amounts and you need to know molecular weights to be able to change it into moles. So here's an example of one that we'll go through. So if you had an HCl solution and you were told it's 36% by mass by HCl, then if you wanted to calculate the mole fraction of HCl in the solution, the first thing you want to do is assume, because it's a percentage, that you have 36 grams of HCl per 100 grams total, okay? Because remember, percent is that versus 100. So for percent by mass, we assume that 36 grams for HCl, and then we have 100 grams total. So we need to calculate our molecular weight for hydrochloric acid, HCl, and that's this 36.5 grams value. And so we convert this into moles, or 36 grams of HCl in moles, so it'd be 36 grams times 1 mole per 36.5 grams, that's that molecular weight. And then it tells us we have 0.99 moles of HCl present. We now need to calculate the moles of water. So if we had 100 grams total, we knew 36 grams for HCl, then 100 minus 36 is 64. So that tells us we have 64 grams of water. The molecular weight of water is 18. So we would take that 68 grams, multiply it by 1 mole per 18 grams, and that would give us 3.6 moles of water. So now what we've got done is we've calculated moles of HCl, moles of water, and to do our mole fraction, it would be moles of HCl divided by moles of water plus moles of HCl, and that's the 3.6 and 0.99 in the denominator, and then our 0.99 in the numerator. We go ahead and do that math, and we get a value of 0.22. So once again, mole fraction, we needed to calculate some molecular weights for the compounds that we're looking at. In this case, we wanted to know how much HCl, what that mole fraction was. So we needed to change the amount of HCl we had into moles and divide it by the moles of HCl plus the moles of water. Because it was a mass percent that we had, we could assume that 36 grams of HCl per 100 grams total is what we would be working with. And so we could subtract that 36 from 100 to get how many grams of water were there. Okay, the next two we'll talk about are molarity and molality. So molarity, you should be pretty familiar with because we've been working with that for some time. And that's simply moles of solute per liter of solution. And that's designated by a capital M. Molality is designated by a small m, and that's moles of solute per kilogram of solvent. So a little bit different. So don't get confused. Molarity, moles of solute per liters of solution. Molality, moles of solute per kilograms of solvent. Okay, so the denominators are the same, but the numerators are the same, but the denominators are different. Liters of solution for molarity, kilograms of solvent for molality. And we'll see a little bit later why you would use molality. Because really molarity is the much, much more common one. And that's the one we've been working with last semester and this semester the most. Let's do an example of molarity calculation. And hopefully this will look familiar to you. So if we were going to dissolve 0.68 grams of potassium phosphate into a 1 liter volumetric flask, calculate what the molarity of this resultant solution would be. One thing about preparing molar solutions, you do it in a volumetric flask so that you know what that total volume is. You don't have to figure it out. So in this case, it's a 1 liter volumetric flask. So we were told in the problem that our molecular weight of this potassium phosphate is 136 grams per mole. So we use that information to convert our 0.68 grams into moles. So 1 mole divided by 136 grams, and we multiply that times 0.68. So that's our dimensional analysis where we cancel our grams units out. And now our numerator is in moles. The denominator needs to be in liters. Well, it's easy this time because we were told the total volume is 1 liter. So we just put that 1 liter value in the denominator. And if we go ahead and do the calculation, we get 0.0050 molar potassium phosphate. Now, one thing that might be a little confusing, so I want to mention it, but hopefully it won't confuse you, is that a lot of times these dilute solutions are expressed as millimolar. 1,000 millimolar equals 1 molar. So, and millimolar is written with a small m followed by a capital M. Don't get confused with that small m, because remember I just said small m is molality. In this case, it means milli. So it's, like I said, don't get confused by that. So if we wanted to convert this 0.0050 molar into millimolar, we would use our conversion of 1,000 millimolar equals 1 molar. So in other words, we would multiply it by 1,000. So think of it as if we go up to our molar up here, if we take that decimal point and just move it 3 places to the right, then we see it's 5.0 millimolar potassium phosphate. Like I said, a lot of times when you have these dilute solutions like this, it's expressed as millimolar rather than having those zeros in the front. So molarity, we've been doing that for a while. The key there is you need to take your weight and use your molecular weight of the compound to convert it into moles. And remember that it's moles per liter of solution. And so you want to make sure that that denominator is in units of liters. So when we think about molarity and molality, if the solutions are pretty dilute and the solvent is water, the values are usually pretty similar. As you get more concentrated, then you see some differences. But for dilute solutions, it's usually pretty similar. Molality does not vary with temperature because the mass doesn't change. Molarity technically can vary with temperature because volumes are temperature dependent. To be honest, for most practical purposes, the molarity doesn't really change that much with temperature because normally you're in a room temperature situation. If you have more extreme temperatures, then that would be a bigger deal. What we've been doing in these problems and what we've been doing, last semester and this semester, we've been using dimensional analysis, which we learned early on. And remember, dimensional analysis is just that lining up your units so that you're canceling stuff out. And if you take advantage of that, it makes a lot of these problems a lot easier because if you get the units all worked out, then you're usually able to do the calculation correctly. When we want to go between molality and molarity, go between those, we would have to have the density of the solution. And that's because remember that molality has a moles per weight units. And so that allows us to use a density to do a conversion between moles per weight versus moles per volume, which is what we have in molarity. So there's some homework problems associated with this stuff that we've been talking about. I'd like to go over a few of these with you. So let me get this pulled up here. And the first one is 13.4.1. Okay, so in 13.4.1, we're told the solution is made containing 14.6 grams of methanol, methanol CH3OH, in 184 grams of water. And then we want to calculate mole fraction of methanol, mass percent of methanol, and molality of methanol. So what we're going to do, the first thing I always like to do in these problems is go ahead and calculate out my molecular weights, get that out of the way, because I know I'm going to be needing to convert from grams to moles on some of these questions. So up on top here, I have the molecular weight of methanol is 32 grams per mole, and then below that, the molecular weight of water is 18. So now we're good to go there. We've got that. So in part A, we wanted the mole fraction. And what did we say mole fraction was? Anybody remember that? Yeah.
It's the moles that come from, like, the moles, all the mixes, all the, everything else.
Yeah, it's the moles of the solute, in this case methanol, divided by the moles of the solute in the solid, which is the methanol in the water. So in the numerator here, we took that 14.6 grams and used the molecular weight to find the number of moles there. In the denominator, we have that same calculation representing the moles of the methanol. And then we were told how much water was present. That was 184 grams. And so we use the molecular weight of water to convert that 184 grams into moles. In the denominator, we add those two together, and that's our total number of moles. In the numerator, we add our moles of methanol, and we do that division, and we get 0.0427. In B, we're asked for the mass percent. So a couple things we should know is one is, since it's mass percent, everything's got to be in the same mass units. In this case, we have values in grams, so we're good to go there. It's just a matter of setting it up. So we're told 14.6 grams of methanol. We put that in the numerator. Then the total is that plus the mass of the water, which was 184. That goes in the denominator. We do that. Since it's a percent, we know percent means what?
Out of 100.
Multiply by 100, yep. So if it's a percent, if this was, and so we have times 100 here, and that gives us our mass percent. If this question was, how many part per million of methanol is there in this, what would we do differently? Yes.
Comes by 10 to the 6.
Yep. So instead of, if we wanted part per million, instead of this being this ratio times 100, it would be times 10 to the 6. If we wanted part per billion, instead of 100, it'd be 10 to the 9. So that part per billion stuff, it's pretty much the same as mass percent. It's just what you're multiplying by. You get it in the units you want. And then the last one, we wanted molality. And remember, molality is moles of solute per kilograms of solvent. So in that case, once again, in the numerator, we change our grams to moles using the molecular weight of methanol. And in the bottom, we just need to change that 184 grams of water into kilograms of water, because water is our solvent. And with there, you just need to remember that 1 kilogram is 10 to the third, or 1,000 grams. And do that conversion, and you do that, and you get 2.48 molal. Okay, any questions on that one? Okay, we'll go through a couple more calculations. So let's look at 1343. In this one, they want us to calculate the molarity of several solutions. So the first one is the first one is 0.540 grams of magnesium nitrate into 250 mils of solution. So we're calculating molarity, moles per liter, so we know we're going to have to get stuff into moles. So for this first one, I'm going to go ahead and I'm going to calculate my molecular weight of magnesium nitrate. So one thing to remember here is when you're calculating that molecular weight, we have two NO3 groups. So we have the NO3 in parentheses and then a 2. So that means we've got 2 nitrogens, but we've got 2 times 3 is 6 oxygens. So make sure you add up the right number of oxygens. So if we add all that stuff up, we get 148.3 grams per mole is our molecular weight. We can change our weight of magnesium nitrate into moles by using that molecular weight. And then remember, it's moles per liter, and our volume, our total volume was given in milliliters. So we have to convert this 250 mil total into liters. And once again, using that 10 to the third factor. So we get a value of 0.0146 moles per liter. If we wanted to express that in millimolar, we'd slide that decimal place over to the right 3 places, and it'd be 14.6 millimolar. Okay, the next one, B. Same thing. In this case, we're told we have 22.4 grams of this lithium compound, and it's 125 ml total solution. So think of it as 125 ml volumetric flask. What's a little different about this is we have waters of hydration. Remember last semester we had a lab where we talked about waters of hydration and did that. So you got to be a little careful when we're calculating this molecular weight. So the lithium is pretty easy, the chlorine is pretty easy. We have one of those. But then we get to oxygen, and we've got 4 from the LiClO4. Then we've got 3 waters here, so we've got 3 more from the water. So we've got a total of 7 oxygens. The hydrogen, we've got 2 in each water molecule. We've got 3 water molecules, so that's a total of 6 hydrogens. So if we did our molecular weight calculation correctly, we should get 160.44. And then we can use that value to convert the 22.4 grams into moles. Our volume was 125 mils. We said it needs to be in liters. So we're going to slide that decimal place over to the left 3 places, and that's 0.125 liters. And then we can do our math and get 1.12 molar as our answer. Okay, then the last one, 25 mils of 3.50 molar nitric acid diluted to 0.250 liters. Hopefully this looks familiar to you from last semester. We had this in the lab and we had this in the class. So this is where we use our M1, B1 equals M2, B2, where M's are the molarity and B's are the volumes. So if we're saying that we have 25 mils of 3.5 molar, and we're going to go dilute it to 0.250 mils, what is the new molarity? Well, our M1 is 3.50 molar. The volumes, the key for the volumes is they just need to be in the same units. I chose to go liters, but if you had them both as milliliters, that would be fine. That'll work out too. The key though is we're given them, in the problem, we're given as one of them in mils and one of them in liters. If we just plug them in like that, we're going to get the wrong answer. Either both got to be liters or both milliliters. So as I said, I chose to convert this 25 mils to liters. That's where I get the 0.0250 liters. And so now I set that problem up, and then it's just a matter of solving for M2. And that gives me a value of 0.350 molar. Once again, we did similar calculations to this last semester, so hopefully it looks familiar to you. The molarity calculation should look familiar too, because we've been doing those for a while. Okay, any questions so far? Let's go on to 4.7 then. So in 4.7, we have a sulfuric acid solution containing 571.6 grams of H2SO4 per liter of solution. And it gives us the density as well, which is 1.329 grams per centimeter cubed. What is centimeter cubed equal to? Yes.
1 mil.
1 mil, yeah. So because they gave it to us in centimeter cubed, we're not going to let that confuse us. We know that that's really mils as well. And so that'll be, since we're going to be working in not in centimeters cubed, but in liters and mils and stuff like that. Then they want us to calculate mass percentage, mole fraction, molality, and molarity. So we gotta do everything here. So for the first one, is mass percentage. So what we want to do is we want to calculate mass of H2SO4, we were given that, that's the 571.6 grams. And then we need the mass of the total solution, right? And so that's where us having a density value comes into play, because we were told it's a liter of solution. We weren't told a weight or anything. But for mass percentage, we got to have weight by weight. So what we can do is we can convert our liter into milliliters, knowing that 1,000 mils equals 1 liter, so that's at 10 to the third. So now we've got our denominator into milliliters. Now we can use our density, the 1.329 grams per mil or grams per centimeter cubed. That's where it's important to remember centimeter cubed and mil means the same thing. And so now our units are grams and grams. We're in good shape there. We want a percentage, so we have our times 100, and we see we get 43.0%. Okay, so the next one we wanted was a mole fraction. So for mole fraction, we have to do what? We have to calculate the moles of whatever we're looking for, in this case H2SO4. And then we have to divide that by the moles of that compound plus the moles of whatever else is in there. In this case, that's water and the sulfuric acid. So H2SO4, we can go ahead and calculate that molecular weight here. And we get 98.065 grams per mole. Water's 18 grams per mole. So we've got those. So now we go ahead and we can set up the top part of our equation. So in the top, we're taking our 571.6 grams of H2SO4, and we are converting it into moles. So we got that part. And then that part will also map down to the denominator. So the only thing left to do is solving for how many moles of water are there. So how do we do that? Any guesses? We're told there was 1 liter, right? And we were told there was the density. So down at the very bottom here, what I did is I took 1 liter, which is 1,000 mils, and I multiplied it by the density. So that converts that 1,000 mils into grams of solution. So what that told me is that liter of solution, based on the density information and knowing that I have a total volume of 1 liter, weighs 1,329 grams. Well, I also was told in the beginning of the problem that I had 571.6 grams of H2SO4. So this 1329 value is the sum of the water and the H2SO4. So if I subtract my H2SO4 number from that total, that tells me how many grams of water I have. In this case, that works out to 757.4 grams of water. So, great, I now have a weight for the water. So what I can do is I can take that 757.4 grams of water and using its molecular weight of 18, I can convert it to moles. So now I've got my problem set up where I have moles of H2SO4 in the numerator, moles of H2SO4 plus moles of water in the denominator. And if I go ahead and work out all the math, I wind up with 0.122 as my H2SO4 mole fraction. So the key to solving this one was remembering that I had that density number, that they gave us that in the problem. And so even though I didn't have a way to get to a mass in the moles, because I knew I had 1 liter of solution and because I had that density information, I could use that to calculate total grams of solution and then subtract that amount that was attributed to the H2SO4 to give me how much water was in there. Okay? So that one you had to kind of think it through a little bit more than some of the others, I think. Okay, we still want to calculate molality and molarity. So remember, molality is what? Moles of H2SO4 divided by kilograms of water. So kilograms of solvent. Calculating the moles of H2SO4, we've done that a couple of times. So we got a feel for that. That's that weight. And then divided by the molecular weight. The kilograms of water, well, in the last part of the problem, we calculated how many grams of water were present, right? That was one of the things we had to do to solve part B. So we're going to use that number, that 757.4 grams of water. We're going to use that and convert it to kilograms. So 1,000 grams of water equals 1 kilogram. That's our conversion there. And so now we're in good shape. We have moles of H2SO4 in the numerator, kilograms of solvent, which is water, in the denominator, and we do the math and we get 7.70 molal. So that's the little m there. The only thing left that we didn't ask to calculate is the molarity. And so here we have, once again, converting our grams of H2SO4 to moles. We can do that in our sleep by now because we've done it several times. And then this is an easy one because since it was 1 liter of solution A, we don't have to do anything in the denominator. We're already in the right units of liters. The number is 1, so there's really no math that occurs. And we see that what we did is 5.829 molar H2SO4. So hopefully you're getting kind of a feel for this. I guarantee you some type of calculation like those will be on the quiz. So if you get them, great. If you don't, you might want to spend a little time doing some of the other homework problems or reviewing these. Before I start on colligative properties, does anyone have any questions about those calculations that we went through? Okay, so today, kind of a pain in the neck with the snow and stuff. I know I had a much longer drive than I normally do, but I'll tell you, in terms of the class and colligative properties, it worked out great. Because what you're going to see is, one of the colligative properties is something called freezing point depression. And if you see people out there spreading salt, that's the colligative properties at work. Okay, so we'll talk about that a little bit. So it really worked out well in that respect, is that we have real life examples today of colligative properties helping us get here safely. So we can all say thank you, colligative properties. All right, so what colligative properties are is that there's certain properties that depend only on the quantity, not the identity of the particles. So I always think of it as you need pieces of stuff. No matter what it is, you just need the pieces. And that results in some of these things that you observe. And the 4 most common ones that people talk about are vapor pressure lowering, or vapor pressure depression, boiling point elevation, freezing point depression, and osmotic pressure. So boiling point elevation, that's one that you commonly see all the time. Like if you ever make spaghetti and they say put salt in, that's to do boiling point elevation. That makes the water a little bit hotter when it boils. Freezing point depression, I already mentioned, that's you put the salt on, that changes the freezing point of water. It changes it from being 0 degrees C down to something lower, depending on how much salt you put. And that's why you see what looks like the stuff melting. You're lowering that freezing point of the water, and so then it's not ice and hopefully you don't slip. And then osmotic pressure, we'll talk about that. I'll give you 2 examples. One is if you like pickles. I like pickles. And so pickles are an example of this, of osmosis. The other one is that we have on a slide is actually, talks about red blood cells. A lot of people here are bio majors, so we have the red blood cell example in there. Personally, I like the pickle example better, but that's okay. So let's talk about vapor pressure. That's the other one. And so remember, we covered vapor pressure previously. And vapor pressure is, you've got stuff in solution, and you've got the headspace above it, and there's some equilibrium of molecules that go in that headspace. So in other words, they're volatile, and then there's have that equilibrium going back and forth. And we always say that if you have more stuff in the vapor phase, that's higher vapor pressure, you have more volatile, things like that. When we talk about this, with the vapor pressure of the molecule, of the solution, we have the forces, the attraction forces within the solvent. So the solvent molecules have a certain level of attraction to each other. When we put something in there, some solute, well, now you also have the attractive forces between the solute molecules amongst themselves, and then finally the solute and the solvent molecules. So all of these are competing at the same time. Those solute-solvent intermolecular attractions, the more you have of those, the less likely the solvent molecules are to then go into the vapor phase. And that's what we're talking about in terms of this vapor pressure reduction. So if you have solvent, and here, let's look at the figures below. So here we have a solvent that has a certain amount of volatility to it. So we have the molecules down in solution, and we have some in the vapor phase, and we have that equilibrium going on, so that steady state. Well, now we go ahead, and if we think of these red balls as the solute, and that solute that we put in is not volatile. So it goes in and it stays in solution. It's not volatile, so it doesn't want to come out. Well, what it does do, it gives us solute-solvent interactions. And so in other words, it ties up in those interactions some of the solvent molecules, so less solvent molecules go into the vapor phase. Now, eventually that's going to reach equilibrium, but the result is if more things are tied up in the solution with that solute molecule and the solvent, then there's less solvent molecules in the headspace. And the end result is we've lowered the vapor pressure of that solvent. So if you had the solvent and you had the solvent with some of these particles in it, and you measured the vapor pressure, it would be lower for the ones that had the solute particles, the non-volatile solute particles in it. There's a way to explain this, and it's called Raoult's law, and that's what we have here. And what we say is that the vapor pressure of a solution is equal to the mole fraction of the solvent times what the vapor pressure of the pure solvent would be. So you could go ahead and you could calculate what the impact of what you added was to it by doing this mole fraction calculation and then knowing what that vapor pressure of the pure solvent is. We also say that if we usually say it's an ideal solution, and so each substance will follow Raoult's law when it's mixed. Key there is an ideal solution. Okay, so boiling point elevation. I gave the example of, putting salt in the water to make it boil a little hotter. And the reason for this is what we just talked about. When we put the stuff in there, it lowers the vapor pressure, okay? So since the vapor pressure is lowered for the solutions, it requires more energy to get it to boil. So if it's more energy, it's going to be a higher temperature. Because remember, to get it to boil, we got to reach atmospheric pressure. So if we lowered that vapor pressure, we're starting from a lower spot, and the atmospheric pressure hasn't changed. So now that difference is bigger. And so to get that up to that pressure that we need, we had to put more energy in. More energy in means higher temperature, and thus the boiling point is raised. Down at the bottom here, there's a phase diagram, which kind of shows you that visually a little bit. You can take a look at that if you like. I'm more interested in just the statement up above. Vapor pressure is lower for these solutions, and because of that, it requires a higher temperature to reach atmospheric pressure, and thus your boiling point is raised. That's the key takeaway in my mind for this. Phase diagram is fine, but that idea of you're raising the boiling point by putting pieces in there, particles in there. Same thing with freezing point. Freezing point is lowered as the boiling point is raised. And here's the phase diagram if you want to take a look at that. But the key is that's the idea, like I said, with outside, why people are putting salt down, is that salt dissociates in there. Those pieces result in it be a lower freezing point. And so if the freezing point is no longer 0 degrees, it's now -5 or something like that. And a lot of times that's enough difference to have things melt. You may hear sometimes it gets so cold that the salt doesn't work. You may have heard them say that on TV before. And so that's just a case of where whatever that delta is that the salt's able to give you, if you're below that temperature, then it doesn't matter. If it's -10 and you dropped it to -5, it's still going to be frozen, right? So you haven't, it's not that you haven't changed it, it's just you haven't changed it enough. So thank goodness for that snow and ice today, right? So you can do a calculation with regards to this boiling point elevation and freezing point depression that allows you to see based on what you put in and concentrations and things like that, what that new temperature will be, that new boiling point or new freezing point. And what we see is that the change in temperature is directly proportional to molality. And one of the things in that proportionality is something called the Van Hoff factor. And the Van Hoff factor, which is represented in the formula by this small case I, is just the number of particles that a substance becomes when it dissolves, when it goes into the solution. And remember in the past, we talked about strong electrolytes and non-electrolytes. Strong electrolytes were the things that totally dissociated. So a lot of times it dissociated into two things, like with the salt, sodium chloride, you get sodium cation, chloride anion. So you have one sodium chloride molecule giving you two pieces, right? The sodium ion and the chloride ion. If you took sugar and put it into water, the sugar doesn't dissociate. It dissolves, but it doesn't associate. So one sugar molecule gives you one piece. So that's what this Van Hoff term is in the formula. So if it's a non-electrolyte, that I value is 1. If it is an electrolyte, a strong electrolyte, then it's at least 2. It could be bigger, just depending upon what the molecular formula is. Sodium chloride example, it would be 2. If you had something that had a different stoichiometry in the molecule, it might be 3 or 4 or something like that. The other terms in these equations, the Kb and Kf, those are just molal, boiling point elevation constant, or freezing point depression constant. So that kind of information you have to be given in the problem or have a table you could look it up in. And then finally, the last term, the small m, is our friend molality. And once again, that's moles of solute per kilogram of solvent. So this is one of the times where you have to use molality rather than molarity. Vast majority of the time you're using molarity, but in this particular formula, it is molality. So what this would allow you to do is if you knew the concentration and you knew your constant, obviously you would know what you put in, and so you could figure out what that Van Hoff factor should be. You could calculate out how much that boiling point would go up or that freezing point would go down. And then know how, if you added enough stuff to it to get the effect that you wanted. Any questions about any of that? Okay. So let's talk about osmosis. This is where we get to discuss the pickle and the blood cell and all that. So some substances have what we call semi-permeable membrane. And what a semi-permeable membrane means is that some stuff can pass through and other stuff can't. And usually it's a size-based thing. Usually the small stuff can get through, but the larger stuff can't. And usually the stuff that gets through is the solvent. Okay, if you think about water, for instance, that's a pretty small molecule, whereas the other things in the solution, good chance those might be bigger. So this movement of solvent molecules, they move from whichever part of the side of the membrane has low concentration of solute to the side that has high concentration. So, and this movement across that membrane is called osmosis. And so it's not the solute that's moving, it's the solvent that's moving. And that's the important thing to remember. So I'll give you the pickle story. So the pickle story is, think what's a pickle? It's a cucumber, right? And how do you make it? You put that in usually a pretty briny, salty solution. Well, the salt doesn't move into the pickle, the water moves out of the pickle into the solution because the pickle water is trying to dilute out the solution that you put in. And the end result is then the cucumber tastes different because it's lost all that water. The pressure to kind of stop this movement is called osmotic pressure, and we'll talk about that in a little bit. But the key thing to remember here is you have this membrane, some things can pass through, and it's usually the solvent that's moving across, but the solvent is going from the more dilute side to the more concentrated side because it's trying to get those concentrations balanced out. And that's what we're talking about is the pressure associated with that is the osmotic pressure. You can do a calculation to calculate osmotic pressure, and that's what we have here in the formula. We have I, that small I, once again, that's that Van Hoff factor. Capital M, this is capital M, that's what? Molarity, right. Whereas before, the last one we were using molality. R is a friend from the past, that's that ideal gas constant, 0.0821 liters atmosphere per moles Kelvin. So that's one that we have used before. It's made a reappearance here in this osmotic pressure calculation. And then finally T, because our gas constant as Kelvin as the temperature unit, that T has to be in Kelvin as well. So here's where, thinking about dimensional analysis, that's how we know the T's got to be in Kelvin. The concentration is going to be moles per liter. So we got to have all this stuff cancel out on the gas constant to leave us with atmospheres as our osmotic pressure. If we have two solutions that have the same osmotic pressure, so in other words, it's perfectly equilibrium, we're not having any osmosis, we're not having any changes. It doesn't mean we don't have stuff going back and forth, but it just means it's happening at the same pace so that there's no, if you analyze those two sides, we get the same numbers. We wouldn't see a change. So when we talk about these types of solutions, osmosis and all that, there's three terms I'd like you to learn. One is isotonic solutions. So an isotonic solution is one where you have the same osmotic pressure on each side of the membrane. So as I said, you have the solvent going back and forth at the same rate. Doesn't mean it's sitting there doing nothing, but it's It's that equilibrium where it's going back and forth, and so nothing changes. Hypotonic solution means you have lower osmotic pressure. So the solvent will leave this solution at a higher rate and it comes back. And then the third one is hypertonic solution, where you have a higher osmotic pressure and the solvent will enter this solution at a higher rate than it leaves it. So isotonic, hypotonic, and hypertonic. And in a little bit, we'll have, okay, right here we have kind of an example of this with red blood cells. And so red blood cells have semi-permeable membranes. And if you store them in a hypertonic solution, they'll shrivel up. And the reason is the water leaves the cell, and that's what we see here in the bottom. So on the left, we have it in an isotonic solution, so everything's great. We're not shifting the concentration. The second one, that's this hypertonic solution. And so what we see is we have a low concentration inside the red blood cell. We have a higher solute concentration outside. It's trying to dilute that outside out to get it more in balance. And the end result is you start losing all your solid, all your water, in this case, out of the blood cell, and it'll shrivel up, and this is called prenation. If it's the opposite of where the solution that the blood cell is stored in has lower concentration, and it's higher concentration of the solute in the blood cell, then the water is going to come from the outside solution into the blood cell, and it's going to bulge it up, and eventually it could burst. And that's what we call hemolysis. I think most people are familiar, if you haven't at least had them, are familiar with IV solutions. So intravenous solutions, they must be isotonic to the blood. You don't want to have one of these two conditions here that we said. You don't want to be pumping that into you because you could either shrivel up your red blood cells or cause them to burst. And so if you've ever had like some type of medicine that they give you through an infusion or something, they often do it, and it's not just the medicine, it's usually mixed in some type of isotonic solution so that the medicine that they want you to get doesn't mess up your red blood cells. So it's in this matrix that is isotonic, and so it keeps you in this first balanced situation rather than the second or third situations there. So you can decide for yourself if you like this example better or the pickle one. I'm not offended if you choose this one, but. Any questions about the colligative properties before we move on to the next part? Okay, so there's a type of compound called a colloid. And what this means is colloids are when, instead of having the individual ions or molecules, they can kind of merge together and form these bigger molecules. And so these particles are bigger than the individual ions or molecules, but they're not big enough to where they fall to the bottom or precipitate out or things like that. They're kind of floating in there. And they're kind of in between solutions and suspensions. So solutions would be, you mix stuff together and you look at it and it's clear. Okay, I can shine light through it, nothing happens. Suspension would be, I mix stuff together and I can see little things floating in there, right? And if I shine the light would get refracted and go off in another direction. A colloid is kind of in between that. When you look at it, you can't really see anything in there. But if you took like a laser light and shined it in there, you get some refraction. And that would tell you there's something there, even though I really can't see it. So it's kind of in between those. Probably the most famous colloid type of situation is down here in the middle of this table, cow's milk. So cow's milk actually is a bunch of little things floating around in there, but you can't see it, right? It just looks like a white liquid. But if you take light and shine it, it'll refract it. And so, but there's all kinds of other ones as well. You see some examples of them here. And so, but colloids actually have another purpose. And this is what I was saying is you can detect colloids by shining light in. This is called the Tyndall effect. And what they're just showing here is two solutions, they're shining light in. It passes through the first one. The second one, we see a change. That's how we know there's something going on there. Where colloids really come into play, though, is to solubilize things. Remember, I made a big deal about saying, hopefully everyone remembers like dissolves like. So polar things dissolve polar things, non-polar things dissolve non-polar things. That's real important. Well, when you think about a lot of things, a lot of products, and just a lot of things in general, you don't just mix a bunch of polar things together, or you don't just mix a lot of non-polar things together. Sometimes you have combinations of things. Some are polar, some are non-polar. So what do you do to keep it from separating? Remember, we had the hexane water example where the hexane floated on top and the water was on bottom. Well, sometimes you need to have these things that have different polarities together. And so if it's polar, we say it's hydrophilic, that means water loving. If it's non-polar, we say it's hydrophobic and water fearing is what they say. So with these colloids, what you can have is you can have a bunch of these molecules separately and kind of massed together. And what you will have is you can have a portion of the molecule is non-polar and a portion that's polar. And then what happens is they orient each other. All the non-polar parts kind of interact together, all the polar parts interact together. But then what that means is if you put those into a solution, then the polar parts, for instance, could interact with water. The non-polar parts could interact with the non-polar parts in there. And it keeps things, those interactions keep things from precipitating out and stuff like that. And that's the trick that people do, is they use these larger molecules. And like I said, the molecule can be by itself, but usually there's some aggregation of it, like it shows here, is that you get that colloid formation so that then you can kind of bridge that gap. I think of it as kind of like a peacemaker. You got the non-polar people on one side, the polar people on the other side. They don't like each other. They don't mix. But you get this colloid in the middle who can kind of talk to the polar people, kind of talk to the non-polar, and kind of bridges to keep things kind of held together. And that's kind of the neat thing about this type of chemistry. So usually the colloids are polar, non-polar. There are ones where you can put ions on, and then the ions interact. That's a little less common. The polar, non-polar is the more common one. And this actually has a place in the biology world. So colloids are real good for emulsifying fats and oils in aqueous solution. So you think of fats and oils, those are almost always non-polar, but yet you want to put it in water, or it's in water, in your body it's in water, right? So what are some things you can do? Well, here's an example of where we have a stearic acid ion. Stearic acid has this long alkane chain on it here, so this is non-polar. That's the white and the black balls here on the left. And then over on the right, we see red and a black ball there. That's a hydrophilic end, so that's gonna be compatible with the water. And then in our diagram, our picture here, we have an oil droplet, and what we see is, we see these non-polar chains of the stearic ion interacting with this non-polar droplet. And then the other side, the red, negatively charged red and black side, that's hydrophilic, so that's able to interact with water. So what it does is it keeps things from precipitating out, separating out as much by using this kind of intermediary compound. And so you can have a bunch of them together doing it, you can have them individually doing it. but it's the same idea. So for those colloids, those types of molecules and doing that kind of emulsifier, they call it, things like that, the idea is a molecule that allows you to solubilize things that normally wouldn't be soluble. That's probably the easiest way to think of it. So there's a few homework problems I'd like to go through here, just to review some of this. Before I do that, do we have any questions about any of this stuff? Okay. Okay, the first one, let's look at 13.7.5. So in 13.7.5, we're asked how many grams of ethylene glycol must be added to 1 kilogram of water to produce a solution that freezes at -5. Does anybody know where one use of ethylene glycol is? There's usually some type of glycol in your antifreeze in your car. That's why that doesn't freeze when it gets real cold. Okay, so in this case, we're going to use our formula that we had that can tell us that relationship between what that decrease, in this case, the freezing point is, and then the concentration, and then how well the stuff breaks up that we put in. So a couple things we're going to need. We know we're going to need molality. So if we need molality, then we know we need to have moles. So over here on the right-hand side, we've gone ahead and calculated the molecular weight of ethylene glycol. So that's 62. And then we can use that eventually to calculate moles and molality and all that. So the other thing is, if we look at our formula, we have this constant. We'll have to look that up or be given to us. But this is Van Hoff thing. So the small I. So for ethylene glycol, how do we know if that's a strong electrolyte or not? Any idea? So the way we know, and so the answer is it's not a strong electrolyte. So this Van Hoff number will be 1 because that doesn't dissociate. The way we figure this out is, look how the formula is written, C2H6O2. Because the hydrogens are in here, all lumped together between the carbon and the oxygen, we know it's not going to be dissociated. If one of those hydrogens was out here on the oxygen, so if that was written like COOH, then that would tell me that that's going to be a hydrogen that can be lost, okay? So you have to look at how the molecular formula is written and go by that. So now we know that I value is 1. The KF value, that's something we look up, we're given. We're told -5 is the difference, right? Because we said we're going from 0 to -5 is what we want to do. So then we can solve for our molality, our moles per kilogram of solid. So that's a calculation we can do. So we do that calculation and we get 2.69 moles of ethylene glycol per kilogram of water. Okay. We want an answer in grams, right? So if this is moles per kilogram, and we were told up here that we have a kilogram of water, so we don't have to worry about that. We know that we have 2.69 moles per kilogram of water. So now all we have to do is convert that moles into grams. That goes back to our molecular weight that we can't calculate up front. And so if we take 2.69 moles times 62 grams per mole, that tells us how many grams of this stuff is needed to change that freezing point from 0 to -5. And remember, we could say per kilogram of water, because up in front, we were told, because we have written on top, that's 1 kilogram of water that we're working with. So we didn't have to do any further manipulation of that term. So if you got a liter of water and you want to drop the freezing point, then 167 grams of ethylene glycol into that solution, and then you'll be good to go. Okay. Let's look at 1377. So in 1377, we want to calculate the osmotic pressure formed by dissolving 44.2 milligrams of aspirin in 0.358 liters of water at 25 C. Okay, so we have our formula, I have it written down here. So the calculated osmotic pressure. So we need that Van Hoff term, we need molarity, we need our gas constant, and we need temperature in Kelvin, right? So let's go ahead and calculate our molecular weight of aspirin. We do that and get 180 grams per mole. We change our temperature from degrees C to Kelvin. Remember, you had 273 to the C to get our K value. That's 298. So the only other thing we need to do now is we need to take some of this information and calculate out our molarity value. So molarity is moles per liter. So we have 44.2 milligrams of aspirin. Moles per liter, if we're going to use our molecular weight, that's moles per gram. So we need to express this 44.2 in, not in milligrams, but in grams. And so 44.2 times 10 to the -3rd expresses it in grams. Now we can use that in our molecular weight to get moles in the numerator. In the denominator, we were told 0.358 liters of water. So we're good there. This is a pretty small amount of aspirin that we're adding, so it's really not going to impact that total volume. So we don't have to correct for that. So we have 0.358 liters. And now we see that here is our value for molarity. The 6.86 times 10 to the -4. We go ahead and plug this stuff in. So why didn't I say the Van Hoff was 1? Why didn't I say it was 2 or something? Why?
Because aspirin has the H in the middle.
Yeah, because the aspirin, the way it's written, has that H in the middle, so that's telling me that the way that's written, it's, the formula is telling me that I don't, it's not going to break into an electrolyte. It's not an electrolyte. It's not going to break into pieces. So I have 1 there for that. I have my molarity, which I just calculated. The gas constant, 0.0821. And then my temperature expressed in Kelvin. I go ahead and do that math and I get 0.0168 atmospheres. Okay, any questions on that? Yes.
You'll, in like the previous version, you'll be given the K, like the constant of the freezing melting point.
You're talking about this one? You're talking about here, this?
1.86.
You would be given that, yes. You would be given that constant in that problem, whether it was a freezing or boiling. In this one, you would be expected to know this constant, this gas law constant, just because we've had that a bunch, and that's a pretty common one. That other one, in reality, is kind of a weirdo one, and so people just look those up. But this is one that gets used a lot, got used in those ideal gas law calculations we did in the past. It's used in this. So that's what I would expect you to know. Okay, any other questions? All right. Okay, the last thing I want to just talk about is you know, we talked about those colloids and emulsifying and things like that. And remember, that's where the colloid helps you get polar and non-polar things kind of a little more friendly towards each other. So if we have these 4 different compounds here, which one do we think would be the best emulsifying agent? So in this case, something I want to point out here, the hydrogen is on the end like that. And so this, and you don't need to know this, but I'll just tell you, this COOH, that's represents what's called a carboxyl group. So you have the carbon, and you have a double bonded O on it, then you have an O bonded to the carbon, and then the hydrogen bonded to that O. And that proton carboxyl groups, depending on the pH, you can lose it pretty easily. That's more information than you need, but I just wanted to explain that. So, but what we have here is the first one, we have CH3, which is nonpolar. We have the COOH, which is polar. The next one, we have CH3, CH2, CH2. That's nonpolar. The right-hand side of the carboxyl group again is polar. Then we have CH3, then we have 11 CH2 groups, then COOH, and then finally CH3, 11 CH2 groups, then COONA. What this means is the oxygen here, the second oxygen is negatively charged, and the sodium is positively charged. So that's a salt, sodium salt there. And so if you think about what we said about emulsifying agents, we said that they have a nonpolar side to interact with those, and then we have it as a polar side to interact with the polar stuff. And so if we look at this and we look at the first two, well, those each have a polar and nonpolar side, so that's great. But the first one just has a little bit of nonpolar, second one a little more, but now we get to these last two, and we got a pretty long chaining. So those interactions are going to be more significant than the first two. So we can pretty quickly, I think, rule out the first two as the best emulsifying agent. But we get to the next two, that's where it gets a little trickier, because they both have the same nonpolar group, the C12 group, and then they both have a carboxyl type situation on the other side. So they both have a nice nonpolar chunk and a nice polar chunk. So they both will probably work pretty well. So why am I saying best choice is the one with the sodium? Any thoughts on that? Well, the reason is, when I put this in water, or whatever the solution is, these are going to dissociate, the COOO minus and the Na plus. And so that is going to be even more polar than with that one above it, where the hydrogen is still there. The hydrogen might leave, but it's going to depend on the pH. We're not given any information about that in the problem. So that's why this last one is the best choice. We have a nice nonpolar part that can partition into the hydrophobic part, and a nice polar part which can go into hydrophilic stuff. Now, what I would say is this is a little tricky deciding between these two, probably not what I would expect out of Gen Chem students, but you definitely should be able to say which is better of these last two or the first two, okay? Because the general theme is part of it's nonpolar, part of it's polar, those interactions, okay? Any questions on this or any of the other stuff we covered today? Okay, if not, then just a reminder that Thursday of this week, we will have a quiz on chapter 13. That's the chapter we just finished. So I would suggest, work through some of the problems, take a look at some of the stuff. We'll have a quiz on Thursday. We'll also start chapter 14 on Thursday. All right, thank you.
Do you have an open book after every class, or do you just have one open for every class?